Hey, chemistry students. I'm going to do a little video here to just review everything that we've learned about single kinds of particles in interaction with their world. And we're kind of setting the stage now for starting to look at some different kinds of particles and how they interact with each other. So it's a good time to just review what we know so far. So we're going to take a look at our model right now, and then we'll have something to build on in the next few units. So the first thing that we learned was the law of conservation of mass. And the law of conservation of mass we found by experimentation with several different kinds of systems that if a change happens in a closed system, the mass stays the same. The only times that we saw changes in mass was when we didn't have a closed system. And when we closed the system, we were able to find that the law of conservation of mass to our ability to measure always held. There's an explanation for that. That's called the particle theory, and this is kind of the fundamental idea in all of chemistry, that everything is made up of particles. And those particles, the more of them there are, the more mass there is. So if you have something that weighs more, it's because there's more particles there. And a third idea here in the particle theory is that particles can't leave or enter a closed system, and that's why the mass doesn't change. Even though we can see great changes in the appearance of these substances, we will not see changes in the mass if the system is closed. Another idea behind the particle theory is that the particles are always constantly randomly moving. More about that later. We saw that matter exists in three important states or phases. One of them is solids. Solids have a high density. That's a property that we can observe macroscopically with our eyes. They also have a consistent shape, so they'll be like a cube or a sphere or something like that, or some jagged kind of like a piece of a rock or something like that. But it doesn't change over time. It stays the same shape. And solids also have a consistent volume. Whatever space they take up, they continue to take up that space. Here's the particle theory explanation for those properties of solids. If the particles are arranged in an orderly, structured way, then that means they're going to have a consistent shape. And they're also going to have a consistent volume because they can't deviate from where they are at all. And they'll have a high density because the particles are attracted to each other, so they pack into a small space. Another state or phase of matter is called liquids. Like solids, liquids have a high density. But unlike solids, liquids have a variable shape. So if you pour liquids in different shaped containers, they will take the shape of that container. Liquids also have a consistent volume like solids, so it doesn't matter what container they're in. Even though their shape will change, the amount of space they take up will not. Here's the particle theory explanation for why liquids have these properties. They have high density because, like solids, the particles are attracted to each other enough that they hold together in a compact space. They don't occupy very much space, so there's a lot of weight in a small amount of space. They have a variable shape because now the particles aren't in this rigid, locked structure. Instead, they can move past each other and slip and slide around, and that allows them to conform to the shape of different containers. But they do have a consistent volume because of the fact that they are still attracted to each other enough that they hold together in kind of a fixed space, even though they're not in a fixed structure. Gases are the third phase or state of matter. Gases have low density, so they're unlike both solids and liquids in that way. Gases have a variable shape, so that makes them, in a way, like liquids, because they can move around and take different forms, different shapes. They'll take the shape of their container. But unlike either gases or liquids, unlike either solids or liquids, gases have a variable volume. That means that they will take up the space of whatever container they're in. So they'll spread out to fill any container. Particle theory explanation for this: in the gas phase or the gas state, the particles are so far apart from each other that those attractive forces don't pull them together into a compact space. So that's why they have low density. That's why they can spread out to the shape and the size of any container that they're in. Gases are an interesting thing to study because they have some characteristics that are common to all gases. And so it's valuable for us to take a look at some details of how they behave. And we did that in this previous study. One characteristic that we investigated was how does the pressure respond to how many particles there are there. And what we found was, as long as we didn't change the volume, by packing more particles into a smaller space, by increasing the number of particles, we saw the pressure increase. And it was a straight line relationship. This is called a direct proportionality, and the math behind this looks like this. The pressure, vertical axis, is equal to a constant number, that's the slope of this line, times the number of particles. If you do a little rearrangement of the variables, that means that the ratio of pressure to number of particles does not change. And so whatever happens to the number of particles, the same thing has to happen to the pressure. In other words, if we double the number of particles, the pressure has to double. If we cut the number of particles in half, the pressure has to be cut in half. Here's the particle theory explanation for why this happens. If we puff in one pump full of air particles into this box, we can see the pressure is about 5 to 6 atmospheres. If we count the wall collisions, we see that there's about 40 collisions for every unit of time. Now we pump in twice as many particles. The pressure jumps to about double, from about 6 to about 12. Now if we check the wall collisions also just about doubled. We puff in another pump full of air, the pressure goes up to triple what it started because there are 3 times as many particles now. The wall collision count, also about triple what we started with. So, as long as the particles are in the same space and they're moving at the same speed, the more of them that have to pack into that space, the more often they're going to bump into stuff like each other and the walls of the container, and so the pressure goes up because of that. So it's the collisions of particles that cause pressure. That's the particle theory explanation for pressure. Another property of gases we discovered by investigating how the pressure responds to changes in volume. So we sealed a fixed number of particles into a container, and then we changed the volume by squishing it into a smaller space or allowing the gas to expand into a larger space. And we found a different kind of relationship. This is called an inverse proportionality. And if we take this data and we plot 1 over volume on the horizontal axis instead of volume, we get a straight line relationship. So the equation of that line would be pressure is a constant number times 1 over volume. Or if we multiply both sides by volume, you get this mathematical relationship. Pressure times volume is a constant number. This is called an inverse proportionality. This is different than the last relationship because now whatever happens to one of the variables, the reciprocal of that has to happen to the other variable. So if pressure doubles, volume doesn't double, volume gets cut in half. If volume gets cut to a third, pressure has to triple. Whatever happens to one, the opposite or the reciprocal has to happen to the other in order for us to retain that constant. Here's the particle theory explanation for that. If I have some particles in a box at about 12 atmospheres, it exerts 58 wall collisions, around 60. I'm going to pack them into a smaller space by making the volume half as big. The pressure just about doubles, and the number of wall collisions, well, it also just about doubles. So that is the explanation offered by the particle theory for why this relationship between pressure and volume is inversely proportional. Another thing that we investigated, we modified the temperature and looked at how did the pressure respond. And we found that as long as we didn't allow the volume to change, there was a straight line relationship between the pressure and the temperature. Here's the relationship, that's the equation for this line that we have here. The pressure is equal to a constant number, that's the slope of this line, times the temperature. But there's a vertical intercept. And the reason there's a vertical intercept is because temperatures can go below 0. We don't want that vertical intercept. That makes our math a little bit harder to do. And so chemists came up with a trick to get rid of it. Here's what they did. They realized that the reason that we have negative temperatures is because 0 is not actually where particles stop moving. And our idea is that the bigger the temperature, the faster the particles are moving. And because the particles are moving, they make collisions, and that's why we have pressure in the first place. So if we were to slide this line over and extend the line that we get from our data to see where does the pressure drop to 0, in other words, where do the particles stop moving, we'd have the coldest temperature that you could possibly have. In other words, these particles are not moving anymore. And since temperature is a measure of the speed of the particles, that's the coldest temperature there is. It turns out to be about 273 below zero in the Celsius scale. So to get rid of the vertical intercept, here's what the scientists did. They took that vertical axis and they slid it down to this lowest possible temperature, which is called absolute zero. And they set zero for the new temperature scale there. That temperature scale is named after a guy called Kelvin, and so this is called the Kelvin temperature scale. The size of a Kelvin is the same size as a Celsius degree, it just starts in a different place. It starts at absolute zero. So to translate a Celsius temperature into a Kelvin temperature, we just add 273 to it. Now that we have no vertical intercept, we have a much nicer relationship between these two variables. The ratio of pressure and temperature is constant, just like the ratio of pressure and number of particles. So whatever happens to one of the variables, the exact same thing must happen to the other variable. Here's the particle explanation for this. If we have some particles in a container, we look at the wall collisions and the pressure. Pressure is around 7.5. Wall collisions are about 55. Yeah, somewhere between 55 and 60 probably. So now I'm going to add some energy through heating and increase the temperature. So I was at a 200 Kelvin temperature. I'm going to double it. I'm going to go up to 400 kelvins. As I do that, the particles start moving more rapidly, which causes more collisions with the container just because they have the same amount of space but they're moving faster. By doubling the temperature, you can see that the pressure doubled, went from about 7.5 to about 15. If I check the wall collisions, well, that didn't quite double, it went up. The reason it didn't double is because there's more going on here than just how often the particles collide. If they're moving faster, they also collide harder, and that's also responsible for the increase in pressure. Another relationship that we looked at was the temperature and volume relationship. We found out that if we don't allow the pressure to change, the volume and the temperature are directly proportional to each other. Again, we have to use the Kelvin scale here because we don't want to deal with zeros and below zero temperatures. So this relationship simply is volume over temperature remains constant. So whatever happens to one of these two variables has to also happen to the other variable. What's the particle explanation for this? Well, this is a little more complicated, but we can figure it out. We have a pressure of about 15-ish, almost 16, and wall collisions are about 100 at 200 kelvins. Now I'm going to increase the temperature up to 400 kelvins, so I doubled it, and the pressure doubled, like I would expect. The wall collisions, well, they also about doubled, but not quite because of the collision's strength effect. The only way I can get the pressure to go back down is to increase the volume to give the particles more space so they don't collide with each other as often. By doubling the volume, I'm able to get the pressure to go back down to about 15 or so. And the collisions drop to about what they used to be. So that's the particle explanation. This would be a good time to talk about the difference between laws and theories. Laws describe, so all of these four relationships that we looked at for gases, we don't have to know why they happen to know that they happen. You can do experiments, as we did, and view with our macroscopic eyes that can't see these particles, that these things are true, that the relationship between volume and temperature is directly proportional, or pressure and volume is inversely proportional. We don't have to know why to know that it's true. Those are laws, and so all of these actually have names. They're named laws, like Boyle's law and Charles' law. Theories, on the other hand, don't just describe. Instead, they explain the laws. So these particle explanations that we have, all based on how the particles move around and collide and move faster or slower, those are theories. In fact, it's one unifying theory called the kinetic molecular theory, or we just call it the particle theory. So theories explain things. Laws don't have to explain. They just describe. We also looked at how solids and liquids respond when we add energy to them. A good tool for tracking this is something called a heating curve. We saw that when we put a solid in a container and we track the temperature by adding energy, we saw that at first that solid increased in its temperature. It was just warming up. So that means the particles were moving faster, jiggling around faster, but staying in that solid structure. If we track the energy storage through an LOL chart, we saw that E therm, the amount of energy stored in the motions, the random kinetic motions of the particles, that went up. And that's what happened to the energy that went in through heating as we warmed this up. If we want to quantify how much energy has to be added to cause this temperature change, it depends on three things. It depends on what is the substance, and we use this quantity C to track that. Every substance has its own C. How much is there? Because it takes more energy to make more particles speed up. So that's the M, the mass part. And how much did we cause the temperature to change? Because that makes a difference. So it's these three factors multiplied together that allow us to quantify how much energy was needed. This only happens until we reach the melting point of the substance. And then we hit a flat spot. The temperature does not rise, even though we're adding energy. So E therm can't account for the increase in energy that we saw during this phase change, this change of state from solid to liquid. So that causes us to introduce another energy storage mode called phase energy. Liquids store more energy in the way their particles are arranged than solids do. We call that phase energy, and that's an increase in phase energy when we go through this change of state. Because there's no temperature change, the amount of energy that it takes to do this change depends only on what the substance is and how much of it there is. So how much of it is measured in mass, like before. What the substance is measured by something called the heat of fusion, or the enthalpy change of fusion, delta HFUS here. That's a number that's characteristic of every kind of substance, and we just multiply that by the mass, and we know how much energy was added to cause the phase change. Once it's all liquid, once it's all melted, the liquid can begin to warm up. Now we see a temperature change, and so the energy added is being used to increase thermal energy. Phase energy stays the same because it was liquid before this diagonal segment of the heating curve started, and at the end it's still liquid, so there's no change in its phase, so no change in its phase energy. And we already have seen that the amount of energy that it takes to cause this kind of a change can be quantified by specific heat capacity times the mass times the temperature change. This will be a different C, a different heat capacity for the liquid than for the solid, because they absorb energy at different rates compared to the temperature change that occurs. They're not exactly the same quantities there. After warming to the boiling point, we see another flat spot in the curve, a place where temperature is not changing, but there is a change in phase. So now the water is going, or whatever the substance is going, from the liquid to the gas phase during this flat spot. So again, the energy that's added is not being used to increase thermal energy because the temperature isn't changing. Instead, it's being used to increase the phase energy. Like before, it depends only on the mass, just like for melting, but it's a different quantity. It takes a lot more energy, it turns out, to vaporize a substance than to melt it, because you're moving the particles much farther apart. So we have a different quantity called heat of vaporization, delta H VAP, times the mass, and that will help you quantify how much energy it takes to cause the change. Hopefully this gives you a nice summary of what you've learned so far and sets the stage for helping you now begin to see how substances interact with each other when they're different kind of particles that form compounds, like the one that's spinning above my head right now.